Gravitation. Revision. We perform many activities in our day-to-day life for which we apply force. For example, lifting a book, cycling, hammering a nail into a wall, climbing a staircase, etc. In all these examples, force is being exerted. There are various effects of a force acting on a body. A force can set a stationary body in motion. A force can change the speed of the body. It can change the direction of motion of the body. A force can change the speed as well as the direction of motion of the body. A force can change the shape and size of the body on which it acts. In the previous grade, we have studied different types of forces. Muscular force, mechanical force, gravitational force, magnetic force, frictional force, electrostatic force are the various types of forces. Out of all these types of forces, we are going to study gravitational force in detail. Come then, let us begin with it. If a ball is thrown upwards by applying force, it reaches a certain height and comes down again. When fruits of trees ripen, they fall down. This happens because the earth pulls all the objects towards itself. We know that the force applied by the earth to pull objects towards itself is called gravitational force, and that the Earth's gravitational force acts on every object. In the previous grade, we have learned that gravitational force is a universal force, and it acts not only between two objects on the Earth, but also between two objects in the universe. Come, let us now understand how this force was discovered. The phenomenon of gravitation was discovered by Sir Isaac Newton. It is said that Newton discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not at an angle to the vertical. Why do they not fly off in a horizontal direction? After careful consideration, Newton drew the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is perpendicular to the ground, and thus the apple falls vertically downwards. Note that the distances shown here are not according to scale. The force of gravitation acting on apples on the tree at different heights from the surface of the earth also acts on objects at even greater heights that are much farther away from the earth. This force acts on even farther objects like the other planets and the sun. The earth's gravitational force holds the atmosphere. If there had been no gravitational force, there would have been no atmosphere due to which the living world would not have survived. In the absence of gravitational force, all objects would have floated. An object thrown vertically upwards would have continued to move upwards and would have never fallen on the ground. Introduction to Scientist. Sir Isaac Newton was one of the greatest scientists of recent times. He was born in England. He gave his laws of motion, equations of motion, and theory of gravity in his book Principia. Before this book was written, Kepler had given 3 laws describing planetary motions. However, the reason why planets move in the way described by Kepler's law was not known. Newton, with his theory of gravity, mathematically derived Kepler's laws. In addition to this, Newton did groundbreaking work in several areas, including light, heat, sound, and mathematics. He invented a new branch of mathematics. This is called calculus and has wide-ranging applications in physics and mathematics. He was the first scientist to construct a reflecting telescope. After knowing about the great scientist, let us now proceed to understand the relation between force and motion. We have learned that a force is necessary to change the speed as well as the direction of motion of an object. In the previous grade, we also studied the 3 laws of motion. Do you remember them? Come, let us revise the laws of motion quickly. Newton's first law of motion. An object continues to remain at rest or in a state of uniform motion along a straight line unless an external unbalanced force acts on it. Newton's second law of motion. The rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of the force. Newton's third law of motion. Every action force has an equal and opposite reaction force which acts simultaneously. After revising the laws of motion, let us now study about circular motion. Circular motion and centripetal force. Let us first perform an activity. Let us tie a stone to one end of a string. Now take the other end of the string in the hand and rotate the string so that the stone moves along a circle. On the stone, moving along a circular path, we are applying a force. As long as we are holding the string, we are pulling the stone towards us. That is, towards the center of the circle. If we release the string, the force applied by us on the stone stops acting, and at that instant, the stone flies off along a straight line, which is the tangent to the circle at the position of the stone. The stone goes along the tangent because that is the direction of the velocity of stone at that instant of time. We had performed a similar kind of activity in the previous grade. Do you remember that activity? In that activity, a 5 rupee coin was kept on a rotating circular disc. We observed that as the disc moves with high speed, the coin placed at the edge of the disc is thrown off. When the coin is thrown off from the disc, it is in the direction of the tangent which is perpendicular to the radius of the disc. From the observation of both these activities, it is clear that a force acts on any object moving along a circle and it is directed towards the center of the circle. This force is called centripetal force. The word centripetal means center seeking. That is, the object tries to go towards the center of the circle because of this force. We know that the natural satellite of the Earth, the Moon, goes round it in a definite orbit. During this motion, the direction of the motion of the Moon constantly changes, and so its velocity constantly changes. A force is constantly exerted on the Moon to make it revolve in a specific orbit around the Earth. The Earth directs this force towards its center. If no such attractive force would have existed, then the Moon would have shown linear motion. Like the Moon, Other planets in the solar system too revolve around the Sun in specific orbits. There exists such a force on these revolving planets as well. That is, the Sun must be attracting the planets, including the Earth, towards itself. Come, before we proceed to the next part, let us know about one scientist. Introduction to Scientist. Johannes Kepler was a German astronomer and mathematician. In 1601, Kepler started working as a helper to the famous astronomer Tycho Brahe. After the sudden death of Brahe in 1601, Kepler was appointed as the royal mathematician in his place. He used the observations of the planetary motions made by Brahe to discover the laws of planetary motion. He wrote several books. Kepler's work was later used by Newton in postulating his law of gravitation. Come then, let us study the laws stated by Kepler. Since ancient times, planetary motion had been observed by astronomers. Before Galileo, all observations about the positions of the planets were made with naked eyes. By the 16th century, a lot of data was available about planetary positions and motion. Johannes Kepler studied the data available at that time. He found that the motion of planets follows certain laws. He stated 3 laws describing planetary motion. Before we proceed to study these laws, let us first understand what is an ellipse. Do you know? An ellipse is the curve obtained when a cone is cut by an inclined plane. An ellipse has 2 focal points. F1 and F2 are 2 focal points of the ellipse shown here. The sum of the distances to the 2 focal points from every point on the curve is constant. Here, A, B and C are the points on the ellipse. Thus, AF1 plus AF2 is equal to BF1 plus BF2 is equal to CF1 plus CF2. After learning what is an ellipse, let us now study Kepler's first law. Kepler's first law. The orbit of a planet is an ellipse with the Sun at one of the foci. The elliptical orbit of a planet revolving around the Sun is shown here. The position of the Sun is indicated by the letter S. Kepler's second law. The line joining the planet and the Sun sweeps equal areas in equal intervals of time. AB and CD are the distances covered by the planet in equal intervals of time. After equal intervals of time, the positions of the planet starting from A and C are shown by letters B and D respectively. This means that the straight lines AS and CS sweep equal area in equal interval of time, which means that area ASB is equal to area CSD. Kepler's third law. The square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is its period of revolution, then t square is directly proportional to r cube. That is, t square upon r cube is equal to the constant, which is equal to k. This is equation 1. After studying about ellipse and Kepler's laws, Now it's time for a question-answer session. As shown in the figure, if the area ESF is equal to area ASB, then what will you infer about EF? If the area ESF is equal to area ASB, then the speed of planet between A and B will be maximum, whereas the speed during E and F will be minimum. Kepler obtained these laws simply from the study of the positions of planets obtained by regular observations. But Kepler could not explain why do planets obey these laws. In the next part of this chapter, we shall understand how these laws help Newton in the formulation of his theory of gravitation. Come, let us now move to the next part. Of gravitation. Newton used Kepler's laws, including all other observations, and formulated his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Here, two objects with masses m1 and m2 are shown. The distance between these objects is d. The gravitational force of attraction between these two objects is given by F is directly proportional to the product of m1 and m2. Similarly, F is inversely proportional to d square. Combining both these equations, we get F is proportional to m1 into m2 upon d square. F is equal to g into m1 into m2 upon d square. Here, g is the constant of proportionality and is called the universal gravitational constant. From this equation, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kilogram kept 1 meter apart. G is equal to F into d square upon m1 into m2. From this equation, come let us know the SI unit of universal gravitational constant, for which let us first write the units of force F, distance d, and mass m. Therefore, SI unit of g is equal to Newton into meter square upon kilogram into kilogram. Thus, SI unit of g is equal to Newton meter square per kilogram square. The value of g was first experimentally measured by Henry Cavendish. In SI units, the value of g is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. The value of g does not depend upon the nature and size of the objects. It also does not depend on the nature of the medium between the two objects. Therefore, it is called the universal constant of gravitation. Suppose the value of g would have been twice of its original value. Then what would have happened? What do you think? If the value of g would have been twice of 6.673 into 10 raised to minus 11 Newton meter square per kilogram square, then the gravitational force would have been doubled. provided the masses of two objects and the distance between them is constant. From the equation, F is equal to G into m1 into m2 upon d square, it is clear that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. But if two bodies are not spherical or having irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between two centers of mass. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of any object having uniform density is at its centroid. In Newton's universal law of gravitation, Newton assumed inverse square dependence on distance. He assumed this dependence due to Kepler's third law. Now you must be wondering, how did the Kepler's third law help Newton? To know this, let us first know about the magnitude of centripetal force. Consider an object moving in a circle with constant speed. We have already seen that there exists a force on the object moving in a circle which is directed towards the center of the circle. This force is called the centripetal force. If the mass of the object is denoted by m, radius of the circle is denoted by r, and its speed is denoted by v, then it can be shown that the magnitude of centripetal force is given by m into v square upon r. The magnitude of centripetal force is proved mathematically, which you will learn in higher grades. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equal to m into v square upon r. This is equation 1. Here, m is the mass of planet, v is its speed, and r is the distance of the planet from the sun. The speed of the planet is found out using the period of evolution t and radius r. It is found out using the formula speed is equal to distance travelled upon time taken. In this formula, distance travelled is equal to the distance travelled by the planet in one revolution, which is equal to the perimeter of the orbit, which is equal to 2 pi r. The time taken by the planet is equal to period of revolution, which is equal to t. Therefore, speed of the planet v is equal to perimeter of the orbit upon period of revolution, which is equal to 2 pi r upon t. This is equation 2. Substituting equation 2 in equation 1, we get F is equal to m into 2 pi r upon t, the bracket square upon r. Therefore, F is equal to 4m pi square r upon t square. Multiplying and dividing this equation by r square, we get, therefore, F is equal to 4m pi square upon r square into r cube upon t square. According to Kepler's third law, T square upon R cube is equal to K is equal to constant. Therefore, F is equal to 4m pi square upon R square K. But 4m pi square upon K is a constant. Thus, F is inversely proportional to R square. Thus, Newton concluded that the centripetal force acting between the Sun and the planets, which is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the Sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. This is possible because of the huge masses of planets, stars, and other constituents of the universe. Come, let us understand how to calculate the gravitational force between two objects. Suppose the mass of one object is 4 kilograms and the other 5 kilograms. If the distance between them is 0.5 meter, then let us find out the gravitational force between these two objects. The gravitational force F is found out using the formula F is equal to G into m1 into m2 upon r square. Here, G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. M1 is equal to 4 kilograms. M2 is equal to 5 kilograms. R is equal to 0.5 meter. Substituting all these values, we get F is equal to 6.67 into 10 raised to minus 11 into 4 into 5 upon 0.5 square. Therefore, the gravitational force between two objects, F, is equal to 533.6 into 10 raised to minus 11 Newton. This force is very low to attract the objects towards each other. Now you must have surely understood why these two objects do not get attracted towards each other. Come, let us now solve some numerical examples based on the topics we have learned so far. Set 1. Example 1. Mahendra and Virat are sitting at a distance of 1 meter from each other. Their masses are 75 kilograms and 80 kilograms respectively. What is the gravitational force between them? Answer. Let us first note down the given information. Distance r is equal to 1 meter. Mahendra's mass m1 is equal to 75 kilograms. Virat's mass m2 is equal to 80 kilograms. Universal gravitational constant G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. According to Newton's law, F is equal to G into m1 into m2 upon r square. Substituting the given values in the above formula, we get F is equal to 6.67 into 10 raised to minus 11 into 75 into 80 upon 1 square. Therefore, F is equal to 4.002 into 10 raised to minus 7 Newton. The gravitational force between Mahendra and Virat is 4.002 into 10 raised to minus 7 Newton. This force is very low. If the force of friction between Mahendra and the bench on which he is sitting is 0, then he will start moving towards Virat under the action of this force. His acceleration and the velocity can be calculated using Newton's law of motion. Example 2. In the example, assuming that the bench on which Mahendra is sitting is frictionless, starting with zero velocity, what will be Mahendra's velocity of motion towards Virat after 1 second? Will this velocity change with time, and how? Here's the answer. Let us first note down the given information. In example 1, we calculated the gravitational force acting on Mahendra. It is equal to 4.002 into 10 raised to minus 7 Newton. Mass of Mahendra M1 is equal to 75 kilogram. As Mahendra is sitting on the bench, his initial velocity, that is u, is equal to 0. Time t is equal to 1 second. According to Newton's second law, the acceleration produced by the force on Mahendra, that is A, is equal to F upon m. Therefore, A is equal to 4.002 into 10 raised to minus 7 divided by 75. Therefore, A is equal to 5.34 into 10 raised to minus 9 meter per second square. Now, using Newton's first equation, let us find out the velocity of Mahendra's velocity after 1 second. Newton's first equation is V is equal to U plus A into T. As the initial velocity is 0 and it is assumed that the bench is frictionless, V is equal to 0 plus 5.34 into 10 raised to minus 9 into 1. Therefore, the velocity of Mahendra after 1 second is 5.34 into 10 raised to minus 9 meter per second. You must have surely understood that this is an extremely small velocity which is possible only in the absence of friction. Also, with time, Mahendra will move towards Virat and the distance between them will decrease. According to Newton's universal law of gravitation, if the distance decreases, the gravitational force increases, and due to which acceleration increases as per Newton's second law of motion. Example 3. Assuming the acceleration in example 2 remains constant, how long will Mahendra take to move 1 centimeter towards Virat? Answer. Let us first note down the given information. As Mahendra is sitting on the bench, his initial velocity u is equal to 0. Mahendra's acceleration A is equal to 5.34 into 10 to the power minus 9 meter per second square. Displacement S is equal to 1 centimeter, which is equal to 0.01 meter. Now, using Newton's second equation, let us find out the time required by Mahendra to move 1 centimeter towards Virat. The equation is displacement S is equal to initial velocity u into time t plus 1 upon 2 into acceleration A into time t square. Substituting the given values in the above equation, we get 0.01 is equal to 0 into t plus 1 upon 2 into 5.34 into 10 to the power minus 9 into t square. Therefore, t is equal to 1935.28 seconds. Come, let us now move to the next part.